is impulse machines and what is the reaction machines. So in impulse machines, so clearly I told, so here only, okay, it having the kinetic energy, okay, it is available at the inlet. Okay, so on whatever the pressure, it is constant throughout the turbine. So hence whatever the relative velocity, okay, so or we can call it as the blade angles is same as at inlet as well as outlet. So that is VR1 is equals to VR2. If VR1 is equals to VR2, so we can call it as a degree of reaction is 0. So that we will going to see in the later part. And similarly in reactions machines, okay, so whatever in reaction machines, okay, it has have both kinetic energy as well as pressure energy. But what happens here in reactions machine, whatever the relative velocity, it is not constant, it is varying. Okay, so that's why here we written, so VR1 does not is equals to VR2. Okay, so whatever here the pressure, it is varying from one stage to one, so one blade to another blade, again from another blade to so another blades. Okay. So here what happens, whatever the degree of reaction, it is varying. So that is also we can see at the later. And we discussed what is the degree of reaction, because the degree of reaction is very important to write the different velocity triangles by varying the R. Okay, so it is the ratio of enthalpy drop in the moving blades to the enthalpy drop in the stages. Okay, enthalpy drop in the moving blades, okay, to the enthalpy drop in the stages. So clearly given the equation. Okay, so U1 square R is equals to U1 square minus U2 square plus VR2 square minus VR1 square by V1 square minus V2 square plus U1 square minus U2 square plus VR2 square minus VR1 square. If it is for axial flow turbine, so in axial flow turbines, U1 is equals to U2. Why U1 is equals to U2? Because whatever the diameter, okay, it is lying on the same line. Okay, so that's why we'll get U1 is equals to U2. So finally we'll get the degree of reaction is this equation. So VR2 square minus VR1 square by V1 square minus V2 square plus VR2 square minus VR1 square. And similarly, utilization factor. So utilization factor epsilon, it is defined as, okay, so whatever the ratio of, so energy utilized by energy supplied. Okay, energy utilized by energy supplied. Again, we can write it for axial flow turbines. And later we discussed the relationship between utilization factor epsilon and degree of reaction R for axial flow turbines or axial flow turbines. So here finally we will get epsilon is equals to V1 square minus V2 square by V1 square minus R into V2 square. So this is the relationship between utilization factor epsilon and degree of reaction R. Degree of reaction R. So later we have to see the maximum utilization factor and the blade speed ratio. So what I told, if we go to the hydraulic turbines, okay, in hydraulic turbines, okay, this blade speed ratio is very important, because okay, you will get one question, that is design a Pelton wheel. Okay, in that, what is the blade speed ratio and all, okay, we have to assume. So for that, okay, for that at least we have to derive this derivation. But before going to this derivation, so here I written the combined velocity triangle by using common base as well as the common apex. Okay, one is the common base, another one is a common apex. So this is the common apex. Got it? So today I will going to teach. See, it is not an important, but wherever, okay, wherever we can use the common apex, so there we can write the combined velocity triangle, and wherever we can draw on the common base. Okay, so that's right. Today I will going to teach so how to draw the velocity triangle. So that is the combined velocity triangle by common apex and common base. Okay. So for that, I'll come for here. I hope you, okay, this whiteboard is visible. So anyone unmute
Yes,
and
sir.
it is visible, right?
Yes, sir.
Yeah, okay. So first here I will going to write the separate velocity triangle. So separate inlet velocity triangle and separate outlet velocity triangle. So later I will going to combine by using common apex and by common base. Okay. So first, so please practice along with me. Okay. So just practice along with me. So here I will going to write inlet velocity triangle. Okay. So here I will going to write inlet velocity triangle. So this is, so it will take time, no problem. So next here I will going to write, so this is B1 and next I will going to write, so this is BR1 and whatever this angle it is, beta 1. So this is beta 1 and next this is alpha 1. This is alpha 1. So next we want from year to year, from year to year it is U1. So next from year to year it is BU1. BU1. Right? So this is inlet velocity triangle. Okay, so you're going to write inlet velocity triangle. This is inlet. Okay, so the same here we're going to draw the outlet. Okay, same, the same colors. Okay, I'm going to use draw the outlet velocity triangle. So red color. So this is BF2. So next green color. So whatever this VR2 and this angle is beta 2 and next blue. So this is V2. This is V2 and this angle is alpha 2. Alpha 2. So next we want from year to year. See alpha to VF means okay we will get VU2. So we will get VU2 and next here up to here from alpha to beta it is U2. So this is inlet velocity triangle and this is the outlet velocity triangle. Okay, so now my question is, okay, in these two velocity triangle, okay, which is the common one? Which is the common one? Which is the common one? You just see VF. So VF in some cases I can call it as the flow is constant throughout the turbine. Okay, whatever the flow, okay, VF, okay, it is constant throughout the turbine. Suppose if I call, so the flow velocity as 10 meter per second throughout the turbine means VF1 is equals to VF2. So here I'm going to write, so VF1 is equals to VF2, so that is equals to VF. I hope you understood why this condition will arise. Okay, the flow, okay, whatever the flow, okay, velocity is constant throughout the turbine. Okay, so they will going to give it is in a 10 meter per second or 8 meter per second, it depends. Okay, so that's why I told in these two, okay, whatever the flow velocity, it is in a common point. Okay, now I will going to draw, okay, the combined velocity triangle by using the common apex. So this is the apex point. Okay, whatever this is the common apex. Okay, so I'll go into right here. I'm going to write here. Okay, next I will take it as a red only. First, I'm going to complete the inlet velocity triangle. First, I'm going to complete the inlet velocity triangle. So this is, and here I'm going to write V1, and this is alpha 1. And next, I want green. So green. So here I'll call it as VR1. This is VR1, okay, and this angle is beta 1. This is beta 1. Okay, next here I'm going to draw from year to year, it is U1. So next up to here, I'm going to call this as a BU1. This is BU1. See, whatever the inlet velocity triangle, I'm writing once again here, but it is the combined velocity triangle, the same. Okay, next, the same, I have to draw the outlet velocity triangle. So the outlet velocity triangle, so I'll call this as B2, and next, so this is beta 2, this is beta 2, and this is a VR, and this is alpha 2. This is alpha 2, and this we can call it as an BF. This is BF. So next we want from year to year. So this I will call it as from alpha to VF2. So we will get BU2. So from year to year, we get U2. You have any doubt here? You just unmute and you tell. You have any doubt here?
No, sir.
No? I hope you understood
No, sir.
how to write the velocity triangle by using the common apex. So here it is a common apex. So here I'm going to write. Whatever this point. Okay, so this is the common apex. Right? See, this is the inlet velocity triangle and this is the outlet velocity triangle. Okay, I just merged because in these two, okay, VF, whatever the flow velocity, it is a common point. And I told clearly, whatever the flow in most of the turbines, okay, throughout the turbine, it is a constant. Okay, whatever the flow velocity in most of the turbines, it is a constant. So that's why here we can see, okay, we just combine the two velocity triangle. Okay, so this is one the common apex. Okay, to draw the velocity triangle. You just see here. You just see here. In this case, okay, so we used it is in a common apex and we draw the velocity triangle. Okay, we draw the velocity triangle. Yeah. So and another one is, okay, so we can use, okay, we can use one more is a the common base. Okay, so here I'm going to show. So next year I'm going to show how to draw the velocity triangle by using the common base. Okay, I think this is visible, right? So here, so first I'm going to draw one reference line. Okay, so I'm going to draw one reference line here. Okay, so next, first I want to start, okay, the inlet velocity triangle. Okay, in this inlet velocity triangle, okay, they has to give what is absolute velocity V1. Next, they has to give what is the nozzle angle, and they has to give what is the U. Okay, so if any problem, okay, means by using the common base, okay, so they has to give what is the absolute velocity and what is the nozzle angle alpha and what is the blade speed velocity. If we know these three data, then easily we can write the velocity triangle. Okay, easily we can write the velocity triangle. Okay, so for that, okay, so I'm going to start from this point. Okay, so I'm going to take, this is the reference point. Okay, this is the reference point. So just now I told, okay, what is alpha? So alpha, suppose if it is on a 20 degree, okay, alpha is 20 degree. Okay, from here, okay, so we have to draw 20 degree and what is absolute velocity? So absolute velocity is 100 meter per second. 100 meter per second. Okay, and what is U? So U is, it is an a 40 meter per second. 40 meter per second. Means whatever it is in a meter per second, so we have to convert into scale. Okay, so 1 centimeter is equals to some 50 meter per second or 100 meter per second. So we have to convert this because in your syllabus you don't have the steam turbines, because in whatever in the steam turbines, okay, we're going to draw the velocity triangle by using graphical method. So this is the graphical method by using the common base. Okay, so this is only for your understanding. Okay, I'm explaining how to draw the velocity triangle here. Okay, so just now I told absolute velocity is 100 meter per second, alpha is 200 degree, sorry 20 degree, and whatever the blade speed velocity u, it is a 40 meter per second. So I took the reference point from here. Okay, from here, okay, first 40 meter per second. So as per your convenient, you can convert the scale. So just now I told 1 centimeter is equals to 20 meter per second, or 1 centimeter is equals to 100 meter per second. It is left to you. Okay, as per your convenient, you can convert the scale. So first I will going to write. So what is u? Okay, for that u, I will going to use this sketch pen. Say from year to year. Okay, so from year to year, so how much is this? So this is 40 meter per second. So here I will going to write it is an a 40. Right, from this point, okay, what is the angle? Angle is 20 degree. Okay, angle is 20 degree. So here from here I will going to draw 20 degree. So this angle I will call it as alpha. So it is an a 20 degree. Clear? So this is 20 degree. And what is V1? What is V1? It is in 100 meter per second. Okay, you just take your compass, okay, or scale. Okay, so just see, I want 100 meter per second. Okay, so I'll going to cut somewhere here. So wherever we will get, okay, I'll going to cut somewhere here, because this is from here to here, the distance is 100 meter per second. Okay, so I'll call this as a V1. So absolute velocity V1. Yeah. Next, I want, so VR1 and I want VF1. See, once we got this point, okay, so if I draw the straight line here, okay, if I am going to draw the straight line here, okay, so I will get, so this is VF. So I will get VF1. Okay, next from this point to, we have to join up to here, because we know 40 meter per second. So u is equals to 40 meter per second. So we can join this line up to here. See, this is VR1, this is VR1, and this angle is beta1. So now we can use your protractor, okay, and check what is the beta angle. So here we are going to write, check what is your beta angle. Okay, next check from here to here what is the distance. So that is VR1. So that is VR1. Okay, next find out or measure the distance for VF1. Find, so VF1. Got it? So this is the graphical method, and whatever here it is same. So I'll going to draw here. So this is from here to here, it is an a U1. Okay, next from here to here it is an a. So this is VF1. Sorry, VU1. So I hope you understood how to draw the velocity triangle by using the common base. So you can unmute and you can ask if you have any doubt. I think no doubt. If you're silent means, so you have no doubt. You understood how to draw the inlet velocity triangle by using the common base? Yes or no?
Yes, sir. Understood.
Understood?
Yes, sir.
Yes, sir.
Okay. Next, in the same velocity triangle only. Okay, once again I have to draw the outlet velocity triangle. Okay, in the same, okay, in the same reference line itself. Okay, I have to draw the outlet velocity triangle. You can answer without any data. So how we can write the outlet velocity triangle? See, while solving the problem, definitely they will going to give. So just now I told, because in most of the turbines, okay, whatever the flow velocity, it is constant. If you measure here, okay, if you will get 10 meter per second, okay, even the, I don't know who is that. Aruja.
Yes,
Yeah,
sir.
yeah, unmute your mic. Yes, thank you. Yeah. Next, while coming to the outlet velocity triangle, okay, definitely we have Vf1 is equals to Vf2, and whatever the Vr1, okay, suppose they will going to give, okay, so if it is in a reaction turbine, okay, they will going to give what is the condition, or if it is in a impulse turbine, so Vr1 is equals to Vr2. Okay, if Vr1 is equals to Vr2, already we measured what is beta. By using this beta, okay, so we can start the velocity triangle here. Okay, so just now I told you, if Vr1 is equals to Vr2, then beta 1 is equals to beta 2. Okay, so then I'll going to start from beta to beta, alpha to alpha. So this is alpha 1. Join this. So whatever this is the alpha 1. Okay, next I want to write the outlet velocity triangle from beta to beta, next from alpha to alpha. Okay, so next I'm going to draw from beta. Okay, so I know the beta value is, okay, it is some 35 degree. It is some 35 degree, and Vr1 is equals to Vr2, because the beta 1 is equals to beta 2. So it is around some 85 meter per second. 85 meter per second. Okay. So I will going to join. So I will going to draw from here. I will going to measure 35 degree. So 35 degree means it will come somewhere here, right? And next I will going to measure 85 meter per second. So 85 meter per second means you will get somewhere here. Okay, you will get somewhere here. Clear? Next, this I will call it as VR2, and whatever this angle, okay, this is beta 2. So here I'm going to show this is beta 2. This is beta 2. Okay, once we know VR, you just see here. Once we know VR, okay, so then I will going to draw one straight line here. So this is, I'll call it as VF. So this is VF2. Okay. Next, once we know VF2, because whatever this distance and this distance is same. Next, we'll going to join from ear to ear. From ear to ear. Okay. So now we got. So this is V2, and whatever this, it is alpha 2. So next we have to measure from ear to ear. Next we have to measure from ear to ear. Because see, already whatever u, okay, it is a common, because beta 2 to alpha 2, it is common, and whatever this, we call it as an a VU2. Okay, so this is the outlet velocity triangle. You just check here. whatever this outlet velocity triangle and whatever it is, both are same. Okay, here U1 is equals to U2. So here I'm going to write U1 is equals to U2 as per the condition. As per the condition. See, whatever these two velocity triangle, okay, whatever these two velocity triangle, okay, I just merged here, whatever this, okay, here. Okay, so here I'm going to show once again here. So like this, and like this. See, this is the inlet velocity triangle, and this is completely outlet velocity triangle. Same. This is VR2, this is VR2, and this is V2, and this is VF2. This is VF2. See, this velocity triangle, okay, I written here. So this is the common base. So if you have any doubt, you can ask. If you have any doubt, you can ask. Outlet velocity triangle. So this is the, by using common apex, and this is the common base. So this is the common base, or we can take it as a reference line. On this reference line, so we can draw the velocity triangle. Okay. So you have any doubt? I think no doubt. Yeah. Okay, then we'll come for, if you understood how to draw the velocity triangle, okay, if you understood, okay, the velocity triangle by using common base and common apex, then I'll move for maximum utilization factor and blade speed ratio. Okay, so before that, before going to this velocity triangle, okay, so we'll going to see the condition. So we want the maximum. When we'll get the maximum? Okay, so whatever the V2, okay, whatever this V2 is nothing but absolute velocity at outlet, it should be a minimum. Okay, if it is a minimum means, okay, we'll going to make it V2 is equals to completely 0. Okay, when we'll get the maximum utilization factor? Okay, when the absolute velocity at outlet, okay, the absolute velocity at outlet, okay, it should be a minimum. Okay, when, because there is a value, but the value is, it is a minimum. So whatever this V2, okay, we'll make it as an a 0. Okay, we're going to make it as an a 0. So then only we will get the maximum utilization factor. Okay, we know. So this is epsilon is equals to V1 square minus V2 square divided by V1 square minus R into V2 square. We know utilization factor we got. Okay, but we want the maximum utilization factor. Okay, when we'll get the maximum utilization factor, whatever the outlet absolute velocity, it should be a minimum. Okay, it should be a minimum. Okay, then only we'll get the maximum utilization factor. Okay, so you just see this velocity triangle. Okay, so we drawn by using the common apex. Okay, we drawn the common apex, but in this velocity triangle you can observe, okay, we don't have V2. Okay, here we don't have the V2. Okay, so you can raise the question, sir, in the VF itself, okay, already you written even V2 also. Yes, I'll come for here. I'll come for here. You can see this common apex velocity triangle. Okay, so here just now I told whatever this V2, okay, whatever this V2, okay, it is in a minimum value. Okay, minimum is some 2 meter per second or some 3 meter per second. So what we did, So completely we written, so V2 is equals to 0. See, if V2 is equals to 0, okay, what about the alpha angle? Even alpha angle is 0. So whatever this alpha 2, it is completely 0. 0, it is 0 means, okay, it is not 0. Okay, whatever this V2, okay, this V2, it is lying on VF. Then whatever this, we will get completely 90 degree. Okay, we'll get 90 degree. Because whatever this line, whatever this V2, okay, V2 it is lying on VF. Okay, V2 is lying on VF. The reason is, okay, V2 is minimum. So I'll come for now this velocity triangle. We can check. So this is inlet velocity triangle. Okay, this is inlet velocity triangle, but while coming to the outlet velocity triangle, we don't have V2. The reason is V2 is minimum. So V2 is equals to, okay, V2 is equals to VF1 is equals to VF2, and V2 will become, sorry, alpha 2 will become 90 degree. Okay, alpha 2 will become 90 degree. The reason is this. Okay, whatever this V2, it is lying on. Okay. So I hope you understood this. Okay, for maximum utilization factor, the value of V2 should be minimum, and from the velocity triangle, it is clearly that V2 is having minimum value when it is an axial. Okay, thus a general velocity diagram for maximum utilization factor is shown above. So shall I continue or you want break? Shall I continue or you want break?
Break, sir.
Okay. So I'll go to take at 1 o'clock, and next I'll going to take up to 1:30 because I have invigilation duty, so I want to go. So next I'll going to start sharp at 1 o'clock. Thank you. Am I audible?
Yes, sir.
Okay, next we'll coming to the maximum utilization factor and blade speed ratio. So first we're going to consider the utilization factor. Okay, so already we derive what is utilization factor. So directly we can use that utilization factor. So epsilon is equals to V1 square minus V2 square by V1 square minus R into V2 square. Okay, so by using this, we have to derive so the maximum utilization factor and the blade speed ratio. Okay, so here first we have to consider the velocity triangle for the maximum utilization. Okay, so first while coming to here, so first by considering this velocity triangle, okay, so we want to know what is this, okay, sine alpha 1 and what is this beta 1. So from the inlet velocity triangle, okay, from the inlet velocity triangle, so what is sine alpha means it is a opposite by adjacent. What is opposite? So opposite is V2, okay, and adjacent is V1. Okay, so sine alpha 1 is opposite by adjacent. So here we will get so V2 by V1. Okay, we got V2 by V1. So then what is V2? So V2 is V1 into sine alpha 1. Okay, so I'm going to call this equation 2. And whatever, and sorry, wherever we have the V2, so we're going to replace it as V1 sine alpha 1. So we can substitute this equation 2 in equation 1. So by substituting this, okay, by substituting this, okay, so directly we can write the maximum. Okay, whatever utilization factor we have, okay, we'll go to write it as a maximum. Why it is in a maximum? Because V2. When V2 is minimum, okay, so we'll get the maximum utilization factor. So we can write, so V1 square minus V2 means, okay, V1 square sine square alpha 1 divided by V1 square minus R into V1 square sine square alpha 1. Okay. In these two, okay, we have V1 square common. Even here also V1 square common. So V1 square will get cancelled. So we will get 1 minus sine square alpha 1 divided by 1 minus R into sine square alpha 1. Okay. So whatever this, okay, whatever this, after cancelling, okay, we will get 1 minus sine square alpha 1. So 1 minus sine, okay, so directly we can write it is an a cos, okay, 1 minus sine, okay, directly we can write it is an a cos, so it is an a 1 minus sine square alpha 1, so we'll get cos square alpha 1 divided by 1 minus r into sine square alpha 1. So this is the maximum utilization factor. Okay, this is the maximum utilization factor. So while solving the problem, okay, so we have to find out, so what is utilization factor? If they ask, okay, we have to find out the maximum utilization factor. So for that, you remember it is in a cos square alpha 1 divided by 1 minus r into sine square alpha 1. Okay. So, and whatever here, okay, utilization factor is equals to unity when alpha 1 is equals to 0. Okay, when alpha 1 is equals to 0. In a such a case, V2 becomes equal to 0. So whatever we have that V2, so that's why V2 should be minimum. Okay, it results with a zero angle turbine. Okay, zero angle turbine. So when we will get this represents an ideal turbine which is impossible to achieve. Okay, it is impossible to achieve. Even though whatever this alpha 1 can be 0, a finite value of V2 with the actual component is necessary to provide the steady flow. Okay, so whatever here, whatever this alpha 1 can be 0, but a finite value of V2 with the actual component is necessary to provide the steady flow. However, this is shows that nozzle angle should be as small as possible. So even while explaining how to draw the velocity triangle, so in that I showed only the nozzle angle. Okay, that is alpha. Okay, it should be a minimum or it should be a small. So it is varying from 0 to 20 or 25 degrees. Okay, whatever that nozzle angle, okay, always it is varying from 0 to 20 or 25 degrees. Okay. Next, the same for impulse turbine. Okay, whatever the maximum utilization factor, okay, we have to draw it for impulse turbine and for 50% reaction turbine. Okay, so for year, okay, for impulse turbine, the degree of reaction is 0. Okay, even in the starting class, okay, general analysis of a turbine, clearly I told R is equals to 0. Okay, so whatever this condition, okay, if we substitute in the above equation, okay, because R is equals to 0. Okay, so we have the cos square alpha 1 divided by 1 minus R into sin square alpha 1. If we substitute R is equals to 0, okay, so whatever this, it completely 0 here. So we'll get cos square alpha 1 by 1. So what is the maximum utilization factor for impulse turbine means it is a cos square alpha 1. Okay, so this is very, very important. Okay, this is very, very important for impulse turbine. So where it is means, okay, in a steam turbines, okay, in a steam turbines, okay, these conditions are very important. Okay, these conditions are very important. Okay, for impulse turbine, R is equals to 0. If we substitute this R here, okay, so we'll get only cos square alpha 1. Okay, so next, we want the blade speed ratio. Okay, so now when consider R is equals to 0, so the relative velocity VR1 is equals to VR2. Okay, from here, from triangle OBC and OCD. Okay, so here triangle OBC, okay, and OCD. Okay, so these two triangles are similar. See, OBC and OCD. Okay, these two triangles are same. By considering this, okay, we want the length U. Okay, whatever the BC, you just see here, whatever this BC, see, BC is U. Why it is U means, okay, because CD, okay, these two are the similar triangles. If the similar triangles, even this distance is also same. See, CD is equals to BC. Okay, this is U. By considering all this, okay, from the geometry of a triangle, what is cos alpha 1? Okay, so we want what is cos alpha 1. So while coming to the cos alpha 1, so we can see AB plus BC. Okay, you just see the here, okay, AB plus, so that is adjacent. Okay, adjacent by hypotenuse. Sorry, opposite by OA. So AB plus BC divided by OA. So what is AB plus BC? U plus U. So we'll get 2U. And what is this adjacent? So it's not adjacent. So this is a hypotenuse. I'm sorry, this is hypotenuse. So it is V1. So cos alpha 1 is, okay, cos alpha 1 is AB plus BC, okay, divided by hypotenuse. So hypotenuse is V1. Okay. By considering this velocity triangle, okay, by considering this, okay, we will get cos alpha 1 is, okay, so it is an a 2 into U by V1. Okay, so 2 into U by V1. So what is U by V1? Okay, so U by V1 we can call it as a blade speed ratio. It is denoted by phi. Okay, blade speed ratio, it is denoted by phi. See, this phi is very important in hydraulic turbines. Okay, so we'll get cos alpha 1 is 2 times phi. Phi is nothing but it is a U by V1. So U by V1 is nothing but it is a blade speed ratio. Okay, then what is phi? So phi is nothing but it is a cos alpha 1 by 2. Okay, phi is cos alpha 1 by 2. So this is the blade speed ratio. One is a maximum utilization factor, another one is a blade speed ratio. And here we have the conditions. Okay, so here we have the conditions. If alpha is 20 degree, okay, if this alpha is 20 degree, then what is the phi value? Okay, so phi value here, just I gave the example here. Okay, if alpha 1 is 20 degree, okay, if I substituted here, okay, if I substituted here, we'll get cos alpha 1 is 0.94 divided by 2. So we'll get phi is 0.47. Okay, suppose if you can use here, it is an alpha is equals to some 15 degree. Okay, then we can check what is the phi value. So what we can call here, it is the trial and error. So that's why whatever this alpha, okay, the nozzle angle, it should be a minimum. Okay, nozzle angle always, okay, it should be a minimum. So if I consider 20 means the phi value, it is varying from 0.47 to 0.5 or 0.48. Okay, so by considering the phi value, so that's why whatever this, it is important in, okay, so hydraulic turbines. Okay, in a hydraulic turbines, because in the hydraulic turbines, especially in Pelton wheel, okay, in Pelton wheel we have the nozzle. Okay, there we have the nozzle. Okay, so this blade speed ratio, okay, we have to consider, or it is varying from 0.46 to 0.48. The reason is the nozzle angle. Alpha, it is from 0 to 20 degree. 20 degree means it is a maximum. Okay, it is a maximum. Okay, so this is for impulse turbine. Okay, the cos square alpha 1 means the maximum utilization factor, and this is for, okay, whatever we got, this is for the axial flow turbines. Okay, so next condition for okay, 50%. Okay, so this derivation I will come later, because so in this stage you won't get what is a 50% reaction turbine. Okay, or it is a 0.5 reaction turbine. So before that, okay, so we should know the velocity triangle for various values of degree of reaction. Okay, so I told clearly by varying the R, where the degree of reaction is varying. Okay, if it is less than 0, if it is a 0, if it is a 0.5, if it is a greater than 0, okay, what we'll get the means the different velocity triangle. Okay, so for this, please remember the degree of reaction for axial flow turbines. Okay, always remember the equation. Okay, R for axial flow turbines. So here you can see, I consider for R degree of reaction for axial flow turbine, because axial flow turbines, okay, U1 is equals to U2. Okay, U1 is equals to U2 means, okay, that will get cancelled. Okay. So the velocity triangle for various value of degree of reaction. Okay, first I will going to consider when R is less than 0. Okay, first case we consider, okay, R is less than 0. Okay, so then I'll going to consider the degree of reaction for axial flow turbines. Okay, R is equals to VR2 square minus VR1 square divided by V1 square minus V2 square plus VR2 square minus VR1 square. What is this What is this? Okay, always we're going to consider it is an energy supplied. Okay, always we're going to consider it is an energy supplied. Okay, so energy supplied. So VR2 square minus VR1 square divided by energy supplied. So if you're going to cross multiply for this, okay, what is R? R is less than 0. Okay, R is less than 0. So in the above equation, if R is less than 0 means, okay, obviously we will get negative. Okay, means R is negative, and whatever the energy is positive. Okay, which is positive? Okay, the whatever we are getting the energy, okay, it is a positive. Okay, so then we can write it as VR2 square minus VR1 square, that is equals to the negative. Why it is a negative means R is less than 0. Okay, if we're going to draw the scale, okay, plus 1, plus 2, plus 3, plus 4. If you write the below, we will get minus 1, minus 2, minus 3. So that's why here also, okay, R is negative. Okay, R is negative. So then whatever this, okay, whatever this we can write it as VR2 square minus VR1 square is equals to negative. Okay, when this is the negative, okay, then this is the negative. So whatever this, okay, whatever this we can transfer this side. Okay, so always VR1 is greater than VR2. Okay, so VR1 is always greater than VR2. Okay, so when VR1 is greater than VR2, when the degree of reaction is less than 0. And less than 0, we will get VR1 is greater than VR2. So for this, okay, for this, we have to write the velocity triangle. So how we will going to draw the velocity triangle for this? Okay, so again, I can use the common apex. See, I'm going to use the common apex, and first I'm going to draw the inlet velocity triangle, but the outlet velocity triangle. So whatever the outlet velocity triangle, whatever here, so usually we're going to draw somewhere here, but instead of writing here, I'm going to write somewhere here. The reason is, okay, VR1 is greater, okay, compared to VR2. Okay, you just see this and this, okay, like this, and here we will get, okay, at the center we will get the VF, but VF, okay, not shown here. Okay, whatever the VF, okay, I'm not shown here. Okay, so this is the velocity triangle. So that's why I explained how to draw the velocity triangle by using the common apex as well as the common base. Okay. So I hope you understood when R is less than 0. Okay, if you have any doubt, you can raise your question. So you have any doubt? You have any doubt? Okay, then next we'll go for when R is equals to 0. Okay, when R is equals to 0. So we discussed for impulse turbine, the degree of reaction is 0. If R is 0, what is the condition? I know. Okay, VR1 is equals to VR2. Okay, VR1 is equals to VR2. So that we have to check here. See, when the second velocity triangle, okay, when the degree of reaction R, if it is a 0. Okay, so once again I will going to draw, once again I will going to write the degree of reaction equation for axial flow turbines. So we'll get VR2 square minus VR1 square divided by V1 square minus V2 square plus VR2 square minus VR1 square. Okay, next I will going to write the condition R is equals to 0. If you cross multiply for this, okay, the complete whatever the energy transfer, it is 0. Okay, whatever this energy equation, this will become 0. Then we will get VR2 square minus VR1 square is equals to 0. Okay, then we have the square here. Okay, so then I can write, so VR2 square is equals to VR1 square. So I can transfer this side. Okay, whatever VR1, I can transfer this side. Okay, so we will get VR2 square is equals to VR1 square. So square square will cancel. Finally, VR1 is equals to VR2. So now you understood, okay, why R is equals to, when R is equals to 0, for that the condition is whatever the relative velocity at inlet is same as the relative velocity at outlet. If relative velocity is same, the blade angle beta, okay, beta 1 is equals to beta 2. Okay, beta 1 is equals to beta 2. Yeah. So for this, okay, I have to write the velocity triangle. Okay, I have to write the velocity triangle. See, you just check it here. Okay, VR1 is equals to VR2. So then how we can write the velocity triangle? Okay, same. Same. Once again, okay, you have to take that velocity triangle. Okay, once again, you have to take the velocity triangle. So then we'll go into right here. Okay. Okay, I'll come back here. So, sir, how we can write the velocity triangle? You don't bother about the velocity triangle. Okay, I'll come for here. Okay, so what is the condition? So, condition is when R is equals to 0, okay, the relative velocity, whatever the relative velocity, VR1 is equals to VR2. So, at that time, beta 1 is equals to beta 2. So, what I will do? So, I'm going to take this. So, here I'm going to write. So, VR1 is equals to VR2. These two are same. These two are same. So you just show here. This is enough. This is enough. Because see, I'm highlighting whatever this is same as this. Okay, and write the condition beta 1 is equals to beta 2. Okay. So that is when R is equals to 0. For R is equals to 0, okay, directly or blindly you can write VR1 is equals to VR2. Okay, if you are getting any confusion, okay, you just write degree of reaction equation for axial flow turbines and substitute here R is equals to 0 and just check it here. What you will get? So you will get VR2 is equals to VR1. Okay, so this is the second one. Okay, by varying the so next, when R is equals to 50%, okay, what is this 0.5? Okay, when the degree of reaction is 50%, usually they are going to call it as a 50% reaction turbine. Okay, for 50% reaction turbine or R is equals to 0.5, okay, what is the condition? Okay, what is the condition? So, and what is the velocity triangle? Okay, while coming to the 50% reaction turbine, okay, so once again I'll use a degree of reaction equation for axial flow turbines. Okay, I'm going to draw here 0.5 is equals to VR2 square minus VR1 square divided by the energy transfer. Okay, so next I just cross multiply here. Okay, we will get 0.5 V1 square minus V2 square plus 0.5 VR2 square minus VR1 square. Got it? So next, here we have VR2 square minus VR1 square. Okay, so once again we have 0.5 VR2 square minus VR1 square here. Okay, so 1 minus 0.5 we will get 0.5 only. So once again I written here 0.5 VR2 square minus VR1 square, that is equals to 0.5 V1 square minus V2 square. So in this case 0.5 will get cancelled. Okay, in this case we'll get 0.5 will get cancelled. Okay, but so here we can write, so whatever this, okay, VR2 square minus V1 square and VR1 square is equals to V2 square. How we will get this one? Okay, so there is a mathematical equation. So A minus X is equals to Y minus B. Okay, so we can write A minus X is equals to Y minus B. Okay, only in the ideal conditions. Okay, so we are assuming, so this VR2 is equals to V1 and VR1 is equals to V2. When we will get this condition? When the degree of reaction is 50%. Because why I am stating this while solving the problems, okay, so you have to remember, when R is equals to 0, VR2 is equals to VR1. When R is equals to 0.5 or 50%, okay, so directly we can write VR1 is equals to V2, okay, and VR2 is equals to V1. Okay, then how we can write the velocity triangle for this? Okay, just see the condition. So V1 is equals to VR2. Okay, V1 is equals to VR2. Okay, so here I written. See, this is the V1. Okay, V1 is equals to VR2 means, okay, this is same as this. So here 1 dash, check it once. This is the 1 dash. And next is VR1 is equals to V2. Okay, so here we have the VR1, see, double dash, and this is V2. So here also double dash. So in this fashion, okay, we have to write the velocity triangle. Okay, in this fashion, so we're going to draw the velocity triangle. Okay, so I hope you understood, okay, how to draw the velocity triangle when R is less than 0, when R is 0, when R is 0.5. Okay, so next, so I'll take another 5 minutes. So I'm going to complete how to draw the velocity triangle. Next, when R is equals to 1. Okay, so next we want R is equals to 1 means the degree of reaction is 100%. Okay, when degree of reaction is 100%, for that R is equals to 1. So what is the conditions we will get? Okay, what is the conditions we will get? So once again, I will going to use the degree of reaction equation. Okay, I will going to use the degree of reaction. Then what is R? R is equals to 1. Okay, I will going to substitute here. R is equals to 1. Okay, so we will get V1 square minus V2 square plus VR2 square minus VR1 square. That is equals to VR2 square minus VR1 square. Okay, so here VR2 and VR2 square minus VR1 square, it will get cancelled. Okay, it will get cancelled. So finally we will get V1 square minus V2 square, that is equals to 0. And finally V1 is equals to V2. Okay, V1 is equals to V2. So for this case, how we can write the velocity triangle? See, instead of writing here V2, okay, so directly we are writing V2 here. Okay, just changing. So I'm going to show here. See, V1 is equals to V2 means, so whatever this, okay, whatever this is coming here and VR2 it is coming here. So in this fashion, okay, we have to change the velocity triangle. See, in the both the manner, okay, in the both the manner, okay, I written the velocity triangle here. Got it? Next, when R is greater than 1, okay, when R is greater than 1, got it? So, for this, what is the conditions we'll get? Okay, means whatever the degree of reaction is greater than 100% means whatever this condition, okay, it is not there, okay, but anyway we have to show this condition. Okay, when degree of reaction, if it is a greater than 100%, okay, what we'll get? So whatever the energy transfer, okay, so whatever this, the energy transfer, okay, always it is greater than, okay, 1 means, okay, whatever the relative velocity, okay, it is maximum to this. Okay, it is in a maximum this. Then, so whatever this equation, okay, VR and VR2, okay, it will get cancelled. Okay, it will get cancelled, and finally we will get whatever the absolute velocity at inlet is less than the absolute velocity at outlet. Okay, when we will get, so when the degree of reaction is greater than 1 means whatever the absolute velocity at outlet is greater, but as per whatever the turbine is running, okay, so always it should be means whatever the absolute velocity, it should be maximum at inlet. Okay, it is in a maximum at inlet. Okay, so whatever this, okay, this condition, it is not that. Okay, so I hope you understood how to draw the velocity triangle by varying the degree of reaction R. Please remember, when R is less than 0, when R is 0, when R is 50%, when R is equals to 100%. Please remember these four conditions. Okay, please remember these four conditions. Okay. If you don't know, please remember this degree of reaction equation for axial flow turbines and check the conditions. As per that condition, draw the velocity triangle. Okay, draw the velocity triangle. Okay. So I'll going to stop here. Okay. So if you have any doubt, so you can raise your question. Okay. So if no doubt, okay, I'm going to wind up here. So I'm going to continue in next class. Okay, I'm going to continue in next class.